So let's take a look at a couple examples. In order to do that, I'm going to move over here. Now this is set up so I can read the slide while I'm doing it. So, for example, let's look at the first problem. It says a helicopter. There we go. A helicopter blade spins at exactly 100 revolutions per minute. Okay. Its tip is exactly 5 meters from the center of rotation. Calculate the average speed of the blade tip. So we have 100. Not writing real good yet. There we go. Divided by 60 revolutions per second, excuse me. And so that's 1.667 revolutions per second. This is seconds per minute here. I wanted to change it to revolutions per second, okay? Now, one revolution, as far as distance is concerned, and if I practice this some more, I'm going to get better at this, is 2 pi r, okay? So the circumference of a circle is 2 pi r, so in this case it's going to be 2 pi times 5, because r is 5, or 10 pi, and pi is 3.14159, so that's 31.4, we'll just round it up to 2 meters. So one revolution is 2 meters, okay? So we're going 31.42 meters, and we're doing 1.667 revolutions in 1 second, and that's meters per revolution. So the revolutions cancel each other out, and you end up with meters per second, which is exactly what we want. So if you multiply these two numbers together, you get the answer. And I don't have my calculator handy here, so I'm not going to be able, hold on. So that's 52 point, and we got 3 significant figures, so that's going to be 0.4 meters per second. So that's the speed. Now this is kind of a trick question, because if something travels in a circle, it starts at this point, goes around, so after a revolution, it's back where it started. So there's no actual displacement. So the velocity is equal to 0 meters per second. So that's the velocity. Okay, now let's look at this second problem. These are the kind of problems, by the way, that you'll see in quizzes and tests. And every once in a while I'll throw you a trick question to make sure you understand the definitions. I don't generally ask a lot of definition-like questions on quizzes and tests, but I'll ask questions in such a way if you don't know the definition, it gets you. So the second one says a commuter backs her car out of her garage with an acceleration of 1.4 meters per second squared. How long does it take to reach the speed of 2 meters per second? Now it doesn't say in the problem here, but an assumption you can make is that V0 is 0 and VF is given at 2 meters per second. And so A is equal to VF minus V0 over T. So AT is equal to VF minus V0. So T is going to equal VF minus V0 over A. And that's going to be 2 minus 0 over 1.4. So T is going to be 1.43 seconds. If she brakes to a stop in 0.8 seconds, what's her deceleration? Okay, so A is equal to VF minus V0 over T. In this case, VF, she brakes to a stop, so VF is 0 minus 2, because she got up to 2 meters per second, and divided by 0.8. And do the math here, and you get 2.5 minus 2.5 meters per second squared. Now, if you have any questions about how I did these two problems, make sure you bring them to class on Monday. Okay, so let's return to our slides now. Now we're going to talk about motion in one dimension. And we've been actually talking about motion in one dimension all along, but we're going to expand what we've been talking about. And in order to do that, we first have to talk about notation. Now this shows that when we talk about the change in time, we usually just write t. We don't write delta t all the time because that can get kind of cumbersome. When we designate something delta x, we're talking about the final position minus the initial or position at time 0. So if we talk about average velocity is delta t or delta x over delta t. So if we rearrange this, moving this delta over here, we have delta x, or the displacement, is going to equal the average velocity times the elapsed time, which makes sense. If you walk 3 miles an hour for an hour, your displacement is 3 miles. So if we substitute for delta x, this expression right here, we write that down there, and we end up with this. Then if we move x0 over, we end up with the final position is equal to the initial position plus the average velocity times the elapsed time, assuming that acceleration has not changed. And this equation is an equation that you need to mark down for future reference, because it'll help you do your problems. Also, at the end of the quarter, when I give you a final exam, I'm going to tell you that you can get a 3x5 card and put any equation you want to on the 3x5 card, or any constant, and that's the only thing you can take in the test with you. This is one of those equations you want to take into the test with you. So let's take a look at an example. You start out with a jogger who runs a straight path at 4 meters per second for 2 minutes. If the initial position is 0, what is the final position? So this is XF. Okay, the final position is XF. So we have XF, or just X, is X0 times the average velocity times the time. And we said we started at the position 0. Then we take 4 meters per second times 2 minutes, but we have to change that 2 minutes to seconds. So it's 120 seconds. So the final position is a positive 480 meters. Okay, so if you start at 0, you're talking about a positive velocity, so that's moving from left to right. So your position is going to start here and end up to the right of that. So this not only tells you the magnitude of this elapsed area, but also the direction in which the person ran. Now if you map or chart an average velocity versus displacement, at any given time you'll be in this setting. So displacement versus velocity for a given time t, and that's what this mapping is. So let's look at another situation. Now we're going to be introducing the idea of acceleration. So not only are we doing this, but now we're looking at the effect of acceleration on the initial velocity. So remember that velocity is equal to the change, acceleration is equal to the change of velocity over time. And if we write that out like we did with the last one, acceleration is equal to Vf minus V0 over t. We move this t over here and we get AT is equal to Vf minus V0. So Vf, or just V, is equal to V0 plus AT if A is constant. So if you want to know the final velocity, if you know the initial velocity and the acceleration in the elapsed time, you can calculate that. This is another equation you want to put in on your card or in your memory bank for something you need to remember. Now let's use this equation. So we had a plane traveling from left to right at 70 meters per second, positive number, and it decelerates, and that deceleration also happens to have a negative sign. It decelerates at 2.5 meters per second squared for 40 seconds. What is the final velocity? So we want to know this. We're going to start with 70 here, and 1.5 here, and 40 here. And I wrote it out here for you. 70 plus a minus 1.5, remember it's minus number, and 40, and we end up that it's going 10 meters per second. So the final velocity after 40 seconds is 10 meters per second. It's still positive, okay? It's still positive. So it's still moving to the right, but at considerably less velocity than it started out. Now let's expand. Let's create a couple of new equations that we can use, and these equations will be so that we can, using velocity and acceleration, we can calculate displacement. So here we have the equation we just did. The final velocity is equal to the initial velocity plus acceleration times time. We also know that the average velocity is equal to the initial velocity plus the final velocity over 2. Now if this is 0, then this becomes 1/2. The average becomes 1/2 of V final. This is also true if A remains constant. So if A remains constant, then whatever this is divided by 2 ends up being the average velocity. So that means that we can take this and divide it by 2 and put it in here, and average is going to equal V0 plus 1/2 AT. So if x, the final position, is x0 plus the average velocity times time, then we can expand this by substituting this in for the average, put that in, do the math, and we get this equation. And lo and behold, this is equations. These two equations are equations we want to put on our card. This one in particular is very important because this gives you the displacement if you know the initial velocity and the acceleration and the elapsed time. So a dragster, here's an example, and a dragster achieves an average acceleration of 26 meters per second squared. Suppose this dragster starts at rest and does this acceleration for this time. How far will the dragster travel? So he starts here, and we're going to arbitrarily call that point 0, and he has no velocity at this point. And we want to know what this point is right over here. So we take the equation we just derived, and we know this V0 is 0. He starts from rest. So that's 0 times the time, 1/2 times the acceleration times the time squared, which ends up being 402 meters. And that's positive, so that means it's traveled from left to right that far. This same dragster, they're asking the question, what is the final velocity of this dragster? So we use an equation that I told you to remember. And this is 0 times this, or plus this factor, the acceleration times the elapsed time, and it's 145 meters per second. So that's the final velocity here. Now if you took 145 minus 0 over 2, you'd have the average velocity. So x minus x0, okay, is equal to the average velocity times the time. We've done that before. Now if we solve this, we also know that the average velocity is equal to the final velocity plus 1/2 the initial velocity. Actually, it's final velocity plus the initial velocity, that whole factor divided by 2. And we take that and multiply, we substitute in this, we multiply the average velocity times the time, and that gives us the displacement. And we work this out, and doing the math, we end up with this equation. And you can work through this math. This is also in your book, by the way. And this is the equation you want to remember. Now, what's the difference? Now, this gives you velocity, and we had another equation that gave us velocity. Well, this gives you the velocity based on the acceleration and the displacement. The other equation gave you the final velocity based on the acceleration and the time. So you use one equation if you know the acceleration and the elapsed time. You use the other equation, this equation, if you know the acceleration and the displacement, or this displacement that has occurred. So that's the difference in how you use these two equations.